One, two, three. Ooh. Hello, folks. I know you're stressed about your midterm, so we may actually finish earlier. I don't want to cram too much into today's lecture. But I do want to start a new topic, and that's the topic of random variables. So we've been talking about random experiments, and we've defined events over those random experiments. We've discussed the concepts of independence, dependence, conditional probabilities, reversing the direction of conditional probabilities, and doing inference. But really we're handicapped until we start talking about random variables. Random variables essentially are functions. So let me just draw the interesting thing about random variables is that they're neither random nor variables. They are actually functions. So if this is my sample space, and let's say I have a discrete sample space, that's how we're going to start most of our discussions until we get to continuous random variables. And let's say these are a few of the sample points that I've enumerated with subscripts. A random variable is a function that takes each of these sample points, that's not what I wanted to do, and maps them to a point along the real axis. So in this course, we're only going to deal with real-valued random variables. In more advanced courses, they bring in complex random variables. We don't deal with those in this class. So if I define a random variable, and we usually define them with capital letters, so x is a random variable. It is a function from the sample space onto the reals. And there's some kind of a rule associated with that function. So that rule will tell you that for any particular omega in your sample space, what particular value the random variable will take. So here, we say that the random variable x takes on the value small x1. Notice I have a capital letter x and a small letter x. The small letter is the particular value of the random variable. Particular value. And x is the random variable. So it's essentially a function. It's a mapping from your sample space onto the reals. Initially, we're going to deal a lot with integer-valued random variables because those are the easiest to deal with. But now, I'll draw a few other mappings. So omega 2, the random variable x will map omega 2 to some other particular value, x1, x2. And it might take x3 and map it to the same place that x1 was mapped. So in this particular case, two different outcomes correspond to the same value of the random variable. What can you not have in this situation? Can I have omega 2 go to another place? I want to see heads moving this way or this way. No. Why? Because it's a function. A function cannot take a value, an element in its domain, and map it to two different values, right? But it can take two different elements in its domain and map it to the same value. Okay, so everything you know about functions hold with random variables. So let's define a few. So actually, let me just sanctify a couple of things we said. So x with the capital letter is the random variable. Small x, or small non-script x, is the particular value of the random variable after a trial of a random experiment of x. And so the way it works is, so in this case, x omega 1 happened to be small x1. x omega 2 happen to be small x2 and so on. And there's a rule that does that mapping. The rule depends on the context, of course, and that's where these examples come in. So let's do an example. Let's say I'm a trader. I go into a trade, let's say a stock, whatever. And this trade either goes my way or it doesn't go my way. Okay? If it goes my way, I make $3. If it doesn't go my way, the $1 I entered, I will lose. Okay? And I have developed a setup that, based on my statistical analysis and backtesting, tells me that with probability P, the trade will go my way. And with probability 1 minus P, I will lose $1. Fair enough? I've got all the software, indicators, everything. I go into fancy chart software. I've set it up so that I know a particular setup will have a probability P of going my way, in which case I make $3. And if it doesn't go my way, I lose $1. Okay? So if x is the random variable of representing the outcome, how many outcomes do I have in my experiment? 2. And what does it remind you of in terms of other random experiments you've seen? Huh? Coin flipping. Yeah. And my random variable will take 2 values. And I'm going to do 2. So this is the random variable x. We'll take on the value -1 with probability, well, I don't want that to be taller. If I'm doing trading, let's make this one taller. Or I make $3 with probability P, or make -$1 or lose $1 with probability 1 minus P. So in this case, my outcomes in the sample space are only 2, omega 1, omega 2, and x of omega 1 is, well, let's make it profit and loss. Well, I don't want to use P for plus or minus. Let's label them this way. And x of plus is simply 3. X of omega minus is -1. This plot here, I'll get to a little later in the lecture. It's a weighting, a way of representing these probabilities for random variables. And it too is a function. I'm going to just label it for now. It's a function of small x. It tells you what values the random variable x can take, and what the likelihood of the random variable x taking each of those values is. So if my random variable is x, at the end of each trade, I'm either at -1 or I'm at my profit or loss is at -1 or 3. It's at -1 with probability 1 minus P. So let's actually put some probabilities here. Let's say this is 0.4, and then this would be not the way I drew it, 0.6 and 0.4. So then this would be 0.4, and this would be 0.6. With probability 0.6, my random variable has value 3, and with probability 0.4, it has value -1. This kind of a trial actually has a name, or this kind of a random variable. It's called a Bernoulli random variable. This is an example of a Bernoulli trial. Strictly speaking, a Bernoulli random variable is defined in this way. It takes on value 1 or 0. It takes on the value 1 with probability P, and the value 0 with probability 1 minus P. So this is a Bernoulli random variable. I'm going to keep using RV for random variable from now on. And if you have a succession of coin tosses, then if you add up these random variables for each of the tosses, what do you get? Let's say 1 represents a success. I flip the coin, or I run the experiment n times. What is the sum of these individual Bernoulli random variables representing? Let's say I do n trades, and in each trade I either succeed, in which case I represent it with the value 1, or I fail, in which case I represent it with value 0. So then let's write this down. Run trial n times. So akin to n coin flips. And let's say on the ith trial, I represent the value as xi. So xi will be 1 if ith flip is a head, success, whatever it is you're measuring. And it's 0 if ith flip is a tail or a failure or a trade that goes against you. So now I'm asking you the following question. Let's see. Now I represent x as a sum of these. xn. What does this new random variable x represent? Number of successes in n trials. So this is the number of successes in n trials. Okay? So I'm introducing you to a bunch of important random variables that are associated with very common and fundamental random experiments and trials. So far we've got Bernoulli, which is simply 1 or 0 with probability p and 1 minus p. We've got, this one is called a binomial random variable, which is a sum of Bernoullis. And even though I haven't really talked about these functions with you, you should be able to tell me what the probability is of having x successes in n trials. So this is the probability that x will be small x. What is the probability that, say, I have 5 successes in 10 tosses? If the tosses are independent. So, talk to your neighbors. Tell me what you think. What is the probability that if I have n of these experiments, I flip a coin n times, each time I measure a 1 or a 0, and then at the end I add up all these numbers. So I have a bunch of 1s and 0s that I'm adding up. That's represented by these xi's here. Okay, so I have a new random variable, which is a sum of n Bernoulli random variables. That's what a binomial is. A binomial is a sum of a bunch of Bernoullis. Now, if I were to ask you, what's the probability that I have, say, 5 successes in n trials, what would you say? Let's make it smaller. Let's say 2 heads in 4 coin flips. How would you do it? Now, first I want you to talk to each other. I didn't hear any commotion here. I know you're all tired and dejected and scared. of this vicious midterm that's coming your way. All right. Did we pick a volunteer last time? Rohan? Go for it, Rohan. So the folks over there can't hear you. If you can speak a little louder. So you're saying how many different ways I can get two heads? So 6 different ways of getting two heads. Okay? So what is the probability of each of those? First tell me how you got this 6. 4 choose 2. I have a total of 4 flips. I want 2 of them to be successes. How many different ways can those successes occur? This goes back to what you're supposed to know for tonight, which is counting, which is 4 choose 2. So there are 4 choose 2. That is 6 ways of getting 2 heads out of 4 flips. Okay. Now each of those has probability what? Okay, so here's where you and I will have to part ways. So each head has probability P. Let's say it's not necessarily a fair coin. P of being a head and 1 minus P of being a tail. And I have 4 independent tosses. 2 of these tosses are heads. That happens with probability what? P squared. And I want exactly 2 heads. So the other 2 have to be what? Tails. And that happens with probability what? 1 minus P squared. So each of those outcomes, this could be the probability of heads, heads, tails, tails. Is this different from the probability of heads, tails, heads, tails? No. So it's also equal to that. In fact, all those 6 different arrangements of the heads and tails has the same probability. So the probability of 2 heads in 4 flips is 4 choose 2 times the individual probability of each of the arrangements. Okay? In general, if I have M Bernoulli trials, N Bernoulli trials, so N coin flips, we want M successes, then the probability that I will have M successes is simply the total number of trials. The number of ways I can have M successes out of N trials is N choose M. And each of those, so tell me how to fill these now. There's a P and there's a 1 minus P. What are the powers here? How many successes? M. So where do I put that? P. Yeah, and the remaining trials have to be failures. This is the probability law for a binomial random variable. sometimes called the distribution. I think in your notes it's called the distribution, and sometimes called the probability mass function, or PMF. PMF is the terminology I grew up on, so you'll find me use it quite often. Okay. So notice, aside from the fact that I've introduced this idea that there's the function that takes your elements in your sample space and maps them to different points along the real line, I haven't really taught you anything new. Everything else we did, especially with this Bernoulli, is based on what you've seen before in terms of coin flips and how to calculate probabilities going to the tail end. And also, I tapped into your basic knowledge of counting. All right. Let's do another example. Any questions on the binomial? Okay, cool. So this is a much simpler example. Roll a fair six-sided die and read the top. So my random variable x is what? X can be any of what values? 1 through 6. Right? And what's the probability that x is a 1? 1/6. And x is a 2? 1/6. And this is true for all the way to x equals 6, which is 1/6. So if I were to draw the probability law or the probability mass function for this, I would just draw a bunch of lollipops from 1, 2, 3, 4, 5, 6. Okay. Notice I'm putting zeros elsewhere because the value of the probability mass function is 0 elsewhere, and it's 1/6 at each of these lollipops. This is a uniform probability mass function or distribution. And it's one of the simplest there is. What do you notice when you add up all these lollipop heights? They add up to 1, because you're accounting for every possible outcome. Okay? All possible values that the random variable can take are accounted for. And even if I go back to the Bernoulli, notice p and 1 minus p. They always added up to 1. You can't have any other, there's no third option. Now let's spice it up a bit and say I roll 2 fair six-sided dice. Fair. So we know how to draw the sample space for that. I haven't defined the random variable that I'm interested in. 1, 2, 3, 4, 5, 6. I have 1 too many. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So, on the same experiment, we can define different random variables. The probability law is fixed for each of the sample points, but the random variables can be defined in any number of ways. So I can, for example, define a random variable x to be the sum of the outcome of the first die and the second die. Okay? I can also define another random variable, call it y, that's the minimum of the two outcomes, of the two rolls. I can make it the maximum of the two rolls. I can even take it as the difference of the first roll and the second roll. The sky is the limit. But let's look at one of these, at least. Let's look at this one. How many possible values can the random variable y take? Everybody? 6. Okay. So, can you help me shade the region in the sample space where the random variable y takes on the value 1? I'm going to use my highlighter here. Tell me where to shade. No, you guys have answered. Go ahead. I saw your hand gesture there. Yeah. You. Yeah. First column and first row. These are all the outcomes that correspond to the random variable y being 1. Okay? And you can probably guess what the outcome, what the points are corresponding to random variable y being 2. Where is that? Where's that next one? Y being 2. Yeah, why don't you continue? Yeah, the next L. These are all the cells corresponding to the random variable y being 2. So, can you help me construct the probability law? So this is y equals 2, and this yellow is y equals 1. And you can go all the way to the top where y equals 6. So, what does the distribution for this look like? You said it has only 6 possible values, so let's label those. 1, 2, 3, 4, 5, 6. What's the probability that the minimum is 6? Let's start from the easy one. Which cell is that? The minimum of the first roll. This is x1. This is x2. What's the actually, I need to be more careful. It has to be small x1 and small x2. What's the probability of the minimum being 6? Which cell is that? Top right. This is the only cell corresponding to the minimum of the 2 rolls being 6. The only way that can happen is if each of them is a 6, correct? The other one can't be anything lower. So, this is 1 over 36. I have a lollipop of height 1 over 36. Okay? And what about 5? It's here, correct? These are the cells corresponding to the minimum being 5. And what's that probability? 1 over. Let's keep the 36 in the denominator so we can, at the end, do a nice sanity check. 3 over 36. And then you have 1, 2, 3, 4, 5. For the minimum being 4. 5 over 36. Then you have 1, 2, 3, 4, 5, 6, 7. Each time you add 2. 36. Then you have 9. And then you have 11 over 36. That became really messy. Now let's make sure that we have, do these add up to 36? 11 and 9, 20, 27, 32, 35, 36. All the lollipops add up to 36 and we're done. So that's the probability law. So when you look at the distribution for random variable y, defined as the minimum of the 2, it favors lower values. because there are more possibilities in the outcome corresponding to the minimum being 1 compared to the minimum being 2 and so on. So this is yet another example where you can define a function that maps the outcomes of your sample space to certain numbers on the real line. In this case, those numbers happen to be the integers 1 through 6. If I had taken the sum of the two random variables, I would have had an integer anywhere between what and what? If I had taken this x here. What are the possible, what happened to the x? What are the possible values of that random variable? Two through 12. The minimum is 2 when each of each die is a 1, and the maximum is 12. So then you would have more outcomes to worry about when you're plotting the probability law for it. Okay. Let's see. So I guess this is a good time for me to actually introduce formally what this probability mass function or probability law is for random variables. I want to make clear that I don't care which notation you use as long as you are clear in communicating to us what notation you use. Each of these is equivalent. Okay? You pick the one you like. I think your notes use the middle one. So the probability that a random variable x, capital X, takes on the value small x in a trial of an experiment is represented symbolically in any of these three ways. Take your pick. That's equal to the probability of all the sample points such that the function, being the random variable, maps each of those sample points to the value x. If you want to get hardcore about it, this is how you write it. So you've got all these small omegas, which are your sample points. You take all the omegas for which the random variable evaluates to small x and add up their probabilities. And what you get is the probability mass function or the distribution at that particular small x. So in our previous example of the two die, the probability that y takes on the value 1 is, what did we do? We did exactly what I've suggested here. We took all the yellow cells, which are all the omegas in my sample space corresponding to the small value 1, and I added their probabilities. Yeah, question? I can't hear you. So the question was, for the purposes of this class, can we assume that a random variable takes a countable set and maps it to a countable set of numbers along the real line? The answer is partially yes. Right now we're dealing with discrete random variables. Soon we're going to get to continuous random variables, and they're a different beast. Because remember, not all sample spaces have a countable set of outcomes. Right? If I have a square of size 1 by 1 square, and I throw a dart somewhere and I measure the x-axis coordinate, that's a continuous random variable. That's no longer a countable set, even though the size is fairly small. But you can think of it the way you just asked about, for discrete random variables. So for the time being, yes, you can. I'm mapping each of these countable outcomes into a set of countable values along the real axis. That's why we call them discrete random variables. We don't use the term probability mass function when we talk about continuous random variables. We use the term probability density function, but we'll get there. So right now, In fact, when we get to the continuous random variable story, I can't say that the probability of the random variable being a particular value is the sum of the probabilities of each of the sample points, because each of those sample points has probability 0. So you're adding a bunch of zeros. So there must be a different way of thinking about those. So in our story here, just to take one example, the probability that the random variable y took on the value 1 is the sum of all the yellow cell probabilities. And that's basically what this means. So all the omegas in my sample space for which the random variable, in our case y, takes on the value 1. That's all the yellow cells. So that ended up being what? 11? 11 over 36. Okay? All right. So far, we've studied the Bernoulli, the binomial. Those are the important ones we've studied. There's another one, which again goes back to the coin toss example. So let's say I did this example when we were talking about drawing sample spaces. Flip a coin until we get first head, or if you want success. Okay? So we flip it. If we get a head, we stop. If we get a tail, we continue. On the second trial, if we get a head, we stop, otherwise we continue. And this was the diagram. Okay, we don't know where it stops. So I'm going to define L as, that's my random variable, number of tosses up to and including first heads or success. Oops. Can you talk to each other and come up with a probability law for this? They're all independent flips. What does it mean? First ask yourself, what does it mean to say that the first head occurred on the small Lth flip or the small Lth Bernoulli trial? What must have happened in the past for me to stop on the Lth flip after I finished the Lth flip? Go for it. Any ideas? Did you raise your hand? I don't want to pick on people today. It's because of the Go ahead. Can you remind me of your name again? Ben. Right. So 1 minus P is the probability of each failure. And I must have had how many of those? L minus 1. Everything up till the very last flip must have been a failure. And then the last flip was a Success. There we go. And this is valid for L equals what to what? You should always label where your formulas apply. For what values of L is this correct? 1, 2, 3, and so on. And it's 0 elsewhere. Okay? This is called a geometric random variable. And it's a very important random variable. So, you have, for you to stop upon the completion of the Lth flip, the Lth flip must have been a success, must have been a head, and the previous L-1 flips must have been tails. Each tail occurs with probability 1 minus p. You've got L independent ones of those, so you just simply multiply those. So you have 1 minus p to the power L minus 1, and then the last flip must be a success, and that's where the p comes from. If you were to plot this, the probability law for this, everything from 0 to the left is 0. At 1, you've got what? What's the value at 1? What's the probability I'll stop on the first flip? I flip the coin, I stop. I stop because I've had a success, I've had a heads. So what's the probability? P. You don't need to plug it into the formula. I mean, that's just from the experiment setup. And then that's 1. Then if I stop at trial 2, the first flip must have been a failure, which is 1 minus p. Second flip must have been a success. So that's the probability. Okay? I'm going to put it in a double parentheses. And it keeps decreasing exponentially. So it's got 1 minus p squared, p for the value 3. And that 1 minus p keeps getting raised to higher and higher powers. 1 minus p is a number smaller than 1, and that's why you have the exponential decay. Okay? And you can verify that this actually satisfies the laws, the principles that you would expect of a probability distribution, which is that every lollipop has to be non-negative, and all the lollipops must add up to 1, right? Every lollipop is non-negative because what? Because of what? What principle? Non-negativity of the probability. There's non-negativity axiom. The probability of any event has to be non-negative. And they all have to add up to 1 because because of what? Total probability has to be 1. Yeah, the probability of the sample space. So it must be true then that 1 minus p to the L minus 1 times p, when I sum it from 1 to infinity, is 1. And I'm going to let you use your power series acrobatics to verify that on your own. But this had better turn out to be true. Any questions on the geometric? I should also show you qualitatively what the binomial looks like. I didn't do that. Let me keep this in the screen still. So just flashback to binomial. We'll revisit this later on when I talk about the Gaussian random variable much later in the course. When you plot the binomial probability mass function, you get, I'm going to draw an envelope, you get lollipops that follow or more progressively more closely follow the bell-shaped curve of the Gaussian or the normal distribution. This is for n large. Remember, the binomial was n trials, n Bernoulli trials, and Bernoulli trials, m successes. So this is the probability mass function for m, and you told me what that was. It was n choose m. N choose m what? One minus p to the n minus m times p to the m. So if you were to plot this for large n, that plot is going to look more and more like the normal distribution, the bell-shaped curve. That has to do with some subtle rules, the law of large numbers and the central limit theorem, and we'll get to those later. But for small number of trials, it's very much dependent on the skew of the probability of the Bernoulli. So if the probability of a success is much higher than the probability of a failure, then this curve is not going to be nice and symmetric. It's going to be skewed. Okay. Any questions on what we did? So we've studied a bunch of important random variables in the discrete realm. We've studied their probability laws. There's still some discrete random variables that I haven't discussed. In particular, the most prominent of them is the Poisson, but we'll get to that a little later. It's a little more complicated than these. Any questions before I move on to the next topic, which is the expected value of a random variable? Boy, I'm the one who hasn't had solid food since yesterday, 8 o'clock. You guys are out of energy. Okay. Expected value of a random variable. So let's go back to that trader example, huh? Let's say I make $3 trading example. I make $3 if the trade goes my way. I lose $1 if the trade goes against me. And this happens with probability P and 1 minus P respectively. Okay? So it's a Bernoulli trial. It's got probability 1 minus P. And I'm going to skew the, this is at -1. And at 3, I've got probability P. And let's call this random variable, I don't know, K. K. Why not? K feels left out. We haven't used it yet. Okay. So, when you look at the plot of the probability mass function, I want you to think about what you learned in very basic physics. Imagine that you have a mass of P at point 3 and a mass of 1 minus P at point -1. And I ask you, where's the center of gravity or the center of mass of this object that consists of the two masses? In other words, where should I put an arrow so that if I were to hold this structure, it would balance? How would you do it? Jack? Plus P times 3. Yeah. I would take the mass at the location where it's sitting and multiplied by its location and multiplied the other mass by its location. And this would be the center of mass. This is what we call the expected value of the random variable x, in this case k, random variable k. So you can think of this as the center of mass. This is the expected value of k, random variable k. And sometimes we just call it its expectation. What are we doing? We're taking the different values and scaling them, doing essentially a convex combination. Right? These coefficients, notice these coefficients are non-negative and they add up to 1. So I'm doing a weighted linear combination of the possible values that the random variable k can take. Random variable k can take the values 3 or minus 1. It takes on the value 3 with the probability p, so I multiply it by that probability. And it takes on the value minus 1 with probability 1 minus p, so I multiply it by 1 minus p in that case. And this linear combination, so this is a convex combination of the values, of the possible values that k can take. That's basically what it is. And if I were to write a formula for it, it would be E of expected value of k is the sum over all possible values that k can take of k times p k small k. So the small k represents the value that the random variable k can take, and it gets scaled by the probability that it takes that value. If I were to write it in the other way that some of you may like, it would be this probability that big K is equal to small k. That's basically what the expected value is. Okay? So each possible value is just weighted by its corresponding probability. That's what's happening. Oh, I can keep it at this. Can you see this font size in the back? Cool. Oh, I had a lot more space than I thought. All I had to do was zoom out. Now let's go back to this example of this poor trader who is doing trading. What's his expected outcome in this case? With probability 1 minus p. Oh no, sorry, wrong one. I don't know what I just read. With probability p, he makes $3. And with probability 1 minus p, he loses $1. Correct? Let me just write that explicitly. That's the expected value of each trial. So what does that simplify to? I have 3p minus 1 plus 1. Plus p. Correct? 4p minus 1. If you were a trader, what would you like this value to be? Above 0 or below 0? Above 0. You don't want to be below 0. So you want this to be non-negative. What should your hit rate be at minimum to break even? What do I mean by hit rate? P, the probability that any trade goes in your favor, right? Or if you want to think in terms of percentages, what percentage of trades should go in your favor? 100p%. So what should that value be? Break-even P. Is what? 1/4. That's what makes this 0. So anything above 1/4, you're doing well on this particular trade setup. If it is true, so it's predicated on the assumption that, in fact, your trade will have a 3-to-1 reward to risk ratio. For every dollar you might possibly lose on a trade, you can win $3. It's predicated on that. If you have a setup that works like that, you only have to be right a quarter of the time to break even. And if you correct 1 out of 3, what happens? What if? Then your expected K is what? 1/3. That's better than Warren Buffett's annual profit rate, which is somewhere in the low 20s. This, by the way, is what kills a lot of traders. That's why 9 out of 10 of them burn out and blow their accounts. Because they care more about the probability of being right than in keeping their losses under control. We all want to be right. You put money on Amazon, you want it to go up or go your way, right? Whereas in fact you have to worry about 2 things. One, your possible maximum risk, and also the probability of being right. Did you have a question, Ben? Ben? Oh, okay. Okay. So that's the basic definition of expected value. Any questions on what we've done? Okay. I'm thinking about letting you... Whoa. Okay, that's my cue. I was going to ask you if you want to be let go or continue with expected value. My computer gave me the answer. So, go relax. Please do not cram until the last minute. It's not a good idea. And I forgot to send you an email insisting that you get enough sleep last night. I hope you did. But all the best to you on the exam. I'll see you on Thursday.
So this is a project sheet that they did yesterday, and it's like, for example, for problem number 2, we have like 5 distinct bins, and we randomly throw 7 identical balls, and it's a uniform probability, and it's saying what is the probability that the first bin has exactly 3 balls in it. And I understand what they did here. It's like 7 choose 3, so we choose which of the 7 balls will go, and then the probability is like 1/5 for those, and then the others I want them to be in a different bin. Right. So 4 or 5. But my question is, could you have done it doing like stars and bars and divide by the total possible outcome? Because we know that we're basically throwing 7 balls into 5 bins. So stars and bars, we know that that's 11 choose 7. The total outcomes. So now it's like, okay, what if I want it to be like, I want to have exactly 3 balls. Then that means I do 7 choose 3 to choose which 3 balls I put into the first one. And then now I have, instead of 7, I have 4 balls and 4 bins. So then that's another stars and bars. So that's 4 and 3, 7 choose 4 divided by the total possible outcomes. But when I put it like into the calculator, like I got a different probability than what this is.
So your 7 choose 3 is the same.
So I'm saying 7 choose 3 to choose which 3 balls I'm placing into the first bin. And then I now exclude that bin, and I have